Hi folks! In this second video on isotope effects, I'm going to be talking more about secondary kinetic isotope effects, steric isotope effects, and equilibrium isotope effects. I want to give a high-level overview of primary compared to secondary kinetic isotope effects. Some of this will be review from the previous video. As a reminder, primary kinetic isotope effects will involve the bond to the isotope breaking or forming. Primary kinetic isotope effects will always be normal, meaning that the KIE will always be greater than or equal to 1. This primary kinetic isotope effect will typically be between 1 and 7. Secondary kinetic isotope effects will not have the bond to the isotope directly breaking or forming in the reaction. Secondary kinetic isotope effects can either be normal or inverse, meaning that they could either be greater than 1 or less than 1. The reasons you might see a secondary kinetic isotope effect are if you have a change in bond hybridization, or the bond is involved in hyperconjugation. Secondary kinetic isotope effects, if they're inverse, will typically be between 0.7 and 1, or if they're normal, they'll be between 1 and 1.4. To understand why secondary kinetic isotope effects arise, we'll need to consider hybridization and its effects on zero-point energies. To do this, we'll have to consider the different modes in which a CH or a CD bond can vibrate, and how this is affected by hybridization. Let's consider a bond between an sp3 hybridized carbon and a hydrogen, and another bond between an sp2 hybridized carbon and a hydrogen. We're not worrying about deuterium yet. The type of vibration that you'd be familiar with from Chem 331 is the stretching vibration. This is where the CH bond is getting shorter and longer as it vibrates and stretches. The sp3 hybridized carbon-hydrogen bond stretches at 2950 inverse centimeters, and the sp2 hybridized carbon-hydrogen bond stretches at 3050 inverse centimeters, approximately. These only differ by 100 wave numbers, so I would call these numbers fairly similar. To understand the effects of hybridization on zero-point energies, we can't just look at stretching vibrations, we have to look at bending ones as well. We didn't talk about these much in Chem 331 because they show up in the fingerprint region, below about 1500. One type of bend, or wag for a molecule, is called an in-plane bend. Imagine that this CH bond is pivoting up and down in the plane of the page. This in-plane bend occurs at 1350 inverse centimeters, regardless of whether the carbon is sp3 or sp2 hybridized. So these are similar values as well. Where you start to see differences between sp3 and sp2 hybridized carbon-hydrogen bonds is in what's known as the out-of-plane bend. This is where you imagine your carbon-hydrogen bond coming up and out of the page, or going into the page as it vibrates. For the sp3 hybridized carbon-hydrogen bond, this bend occurs at 1350 inverse centimeters, the same as for the in-plane bend, whereas things are different for the case of the sp2 hybridized carbon-hydrogen bond. So we have a very large difference in wave numbers for this particular bending mode. It's this bending mode that differs by 550 inverse centimeters that we need to pay attention to for isotope effects and zero-point energies. organic chemists would call this higher frequency vibration stiffer, and they would call this lower frequency vibration looser. For the stiffer vibration for the sp3 hybridized carbon-hydrogen bond, there is a more narrow energy well for the 0-point energies. And for the looser, lower frequency out-of-plane bend for the sp2 hybridized carbon-hydrogen bond, you can think about your vibrational 0-point energy well as being wide and shallow. For the narrow energy well, there is a larger difference in 0-point energies compared to the 0-point energy difference between hydrogen and deuterium for the wider well. Because the narrow well is associated with sp3 hybridization and the wide well is associated with sp2 hybridization, the difference in 0-point energies for an sp3 hybridized carbon-hydrogen or carbon-deuterium bond is less than the 0-point energy difference for an sp2 hybridized carbon-hydrogen versus carbon-deuterium bond. What it means for a vibration to be stiffer and have a narrower energy well is that there's a higher energy penalty from deviating from the ideal angles. You can see this by thinking about the geometries for sp3 versus sp2 carbons. As you take the CH bond and bend it out of the plane of the page, it gets very close to either the wedge or the dash groups also attached to the sp3 hybridized carbon. What this means is that as you deviate this bond angle slightly, your energy shoots up rapidly in your energy well. In contrast, this sp2 hybridized carbon is trigonal planar, and as you bend the CH bond either out of the page or into the page, it doesn't clash with any groups attached to the sp2 hybridized carbon because the sp2 hybridized carbon is planar. Let's consider an example where we're going from carbon sp3 hybridization to sp2 hybridization. An example of this is in the following E2 reaction. The hydrogen that's deprotonated during the E2 elimination reaction is this beta hydrogen, and the hydrogen or deuterium stays attached to the carbon through the whole reaction. Notice that the carbon attached to hydrogen or deuterium is sp3 in the starting material and then sp2 in the alkene product. Because this carbon-hydrogen bond is not breaking, we have a secondary kinetic isotope effect. And in the energy diagram I'm going to show below, I'm going to assume that this reaction is exergonic, because I know that it is spontaneous and favorable, because the products are formed. My energy diagram to start would look like this. On top of this diagram, I'm going to fill in information I know about the 0-point energies for sp3 versus sp2 hybridization, for the starting material and the alkene product. For the starting material, I have an sp3 hybridized carbon-hydrogen or carbon-deuterium bond, and that out-of-plane bend for this bond has a stiff potential energy well. I would draw a relatively narrow well, and I will have a large difference in 0-point energies between deuterium versus hydrogen. For the sp2 hybridized carbon-hydrogen or carbon-deuterium bond in the product, I have a lower frequency out-of-plane bend, and I have a wide energy well corresponding to a small difference in 0-point energies for deuterium compared to hydrogen. Where I need to fill in the gaps is thinking about the transition state. The transition state is being converted between these two hybridization extremes, and it's going to look in between those two extremes as well. I'm drawing it as having a moderate width, and the difference in 0-point energies is in between those for sp3 versus sp2. The barrier for this reaction involving a deuterium can be determined by going from the 0-point energy of deuterium up to the transition state for deuterium. I would call this delta G double dagger for the C-D bond. And I can do the same thing for hydrogen. I measure from the hydrogen energy level starting out up to the hydrogen level of the transition state. You could think about the hydrogen in the starting material having a boost up compared to deuterium due to this large 0-point energy difference. So this delta G double dagger value for hydrogen should be smaller than that for deuterium. This means that the rate of the reaction involving hydrogen will be greater than the rate involving deuterium. When the reaction rate involving hydrogen is higher than that of deuterium, the kinetic isotope effect will be greater than 1, and we'll call it a normal kinetic isotope effect. And typical values that you'll see when going from sp3 to sp2 hybridization for secondary isotope effects will be between 1 and 1.4. Notice that this value for a normal secondary isotope effect is smaller than that for a primary isotope effect, and that's because the hydrogen or deuterium is not directly involved in the reaction, so we can expect that its influence on the rate will be smaller. Now let's consider an example where we're going from an sp2 hybridized carbon to an sp3 hybridized one. We can see this in the nucleophilic attack of an aldehyde using a cyanide nucleophile. The starting carbon that's bound to hydrogen or deuterium is sp2 hybridized, and in the product it has become sp3 hybridized. Because the bond between carbon and hydrogen or deuterium has not changed, we're looking at a secondary kinetic isotope effect. And similar to the last reaction, I'm going to assume that this reaction is exergonic because this reaction does occur, and that's going to give me a starting point for my reaction coordinate diagram. I would have a single transition state along my reaction coordinate diagram, and I'm showing it that the reaction is exergonic. Now we need to think about those 0-point energies and how narrow or wide the wells are at each of the different positions, based on the carbon's hybridization that is bound to hydrogen or deuterium. For the sp2 hybridized carbon starting material, where that carbon is attached to the hydrogen or the deuterium, this CH or CD bond is going to have a loose 0-point energy potential well. The 0-point energies for deuterium versus hydrogen are very close to each other for this sp2 hybridized carbon. For the sp3 hybridized carbon-hydrogen or deuterium bond of the product, I will have a narrow potential energy well. This is for a stiff vibration, and there's a large difference in 0-point energies between deuterium versus hydrogen. Similar to the last example, the transition state is somewhere in between these two extremes. I'm drawing a moderately wide well with a moderate difference in 0-point energies. So now let's think about how much energy would it take to go from the starting material to the transition state when you have a bond to hydrogen or a bond to deuterium. The energy when you have a CD bond present is from this 0-point energy level from deuterium up to the 0-point energy level of deuterium at the transition state. This is my delta G double dagger for my carbon-deuterium bond. Then we can do the same thing for hydrogen. going from the hydrogen 0-point energy level for the starting material up to the hydrogen level at the transition state. Here notice that hydrogen barely has an advantage compared to deuterium in the starting material, but hydrogen is significantly higher in energy than deuterium at the transition state. When this is the case, the barrier for the reaction involving the carbon-hydrogen bond will be greater than the barrier involving the carbon-deuterium bond. This will mean that the rate of the reaction involving the carbon-hydrogen bond will be smaller than the rate involving the carbon-deuterium bond. This is not a scenario we have seen previously. This implies an inverse isotope effect, where the kinetic isotope effect is less than 1. Typical values that you might see for reactions where you're going from sp2 to sp3 hybridization at a carbon that is bound to hydrogen or deuterium are that you might see kinetic isotope effect values between 0.7 and 1. You can also observe secondary kinetic isotope effects when hyperconjugation involving CH compared to CD bonds is involved. Let's consider this following alkyl halide starting material. And let's consider a loss of the bromide leaving group to generate a carbocation. The carbocation itself is sp2 hybridized and trigonal planar, and it has an empty p orbital. Notice that my carbon bond to hydrogen or deuterium is adjacent to this empty p orbital. The electron density from this bond can be donated to stabilize the carbocation through hyperconjugation. This is a donation of electron density from the sigma bond between carbon and hydrogen, or carbon and deuterium, donating into the empty p orbital of the carbocation. This hyperconjugation is going to weaken the carbon-hydrogen or deuterium bond relative to how strong it was in the starting material. And you might see this manifested as a normal and secondary kinetic isotope effect that would be between about 1 and 1.4. Another type of secondary isotope effect is known as steric isotope effects. To see why these arise, let's return to looking at the homolytic cleavage of carbon-hydrogen or carbon-deuterium bonds. If we plot the Gibbs free energy as a function of carbon-hydrogen or carbon-deuterium distance, we get a graph that looks like this. Our lowest energy point corresponds to our typical bond length. Going shorter than this leads to nuclear repulsion and a quick increase in energy, and going longer in this leads to a more steady increase in energy leveling off at some energy corresponding to complete bond cleavage and radical formation. Because of the larger reduced mass for carbon-deuterium compared to carbon-hydrogen, our 0-point energy for the carbon-deuterium bond is lower. In terms of thinking about the bond lengths between carbon and hydrogen or carbon and deuterium, it's useful to think about the shape of this graph. A perfectly symmetrical energy curve would look something like this, and we would call this a harmonic oscillator. And when you have this unsymmetrical shape, you'll have what's known as an anharmonic oscillator. If you looked at the center of the energy well for deuterium, it's further to the left than it is for hydrogen. This point corresponds to the distance of the carbon-deuterium versus the carbon-hydrogen bond. Because this distance is smaller for deuterium, the carbon-deuterium bond is shorter than a carbon-hydrogen bond. And this means that deuterium behaves as if it's smaller than hydrogen. So for example, if you had a CD3 group it would behave as if it's smaller than a CH3 group. I want to end by talking about what are known as equilibrium isotope effects. So far we've been looking at kinetic parameters, where we're comparing zero-point energies for reactants compared to transition states. And what we see is that switching out hydrogen for deuterium leads to changes in reaction rates. Isotopes can also change the equilibrium position for reactions. In this case, it's not going to be as easy to predict what these values should look like, but they will be equilibrium constants instead of rate constants. Let's consider the following equilibrium. In each molecule, I have an aldehyde, an OH group, and an OD group. And the difference is in the placement of the hydrogen versus the deuterium of my alcohol groups. This becomes interesting because the aldehyde that is ortho to one of the alcohols can hydrogen bond with the OH or OD group at this position. I'm calling this a hydrogen bond, but really in this case it could better be called a deuterium bond, but that term is a little bit weird. What's observed is that the KEq in this case is 1.1. Meaning that there is a higher concentration of the product relative to that of the starting material. The placement of hydrogen compared to deuterium in the hydrogen bonding interaction plays a difference. If we think back to IR spectroscopy and frequency and wave number, recall that alcohol groups that are not involved in hydrogen bonding show up at higher wave numbers or higher frequencies. Hydrogen bonding weakens the OH bond. Hydrogen bonding will weaken the OH or OD bond, leading to it having a lower wave number. What's experimentally observed in this case, and again, I wouldn't ask you to predict this, just to analyze some data, the observation in this case is that there's a preference to put deuterium in the stronger and higher frequency alcohol bond that's not participating in hydrogen bonding. And there's a preference for putting the OH bond as the one that is participating in hydrogen bonding. Alright, so in summary, this video followed up on some of the ideas from isotope effects that I introduced previously. I talked about secondary isotope effects in more detail. I also talked about sterics and isotope effects, and introduced the idea of equilibrium isotope effects as well. That's it for this video. I will see you in class.